Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all to the lecture number 9 on the subject of computer organization and assembly language programming. The title of today's session is Design of Arithmetic Logic Unit Part 2. Well, today we will start with a short class quiz. We will talk about different components of a general purpose computer system and we'll see where the ALU fits in this architecture. Since the target of this part of the course is design of the hack computer, so today's target is the design of an ALU for this hack computer. We will write the HDL of this ALU and finally we will verify the ALU chip logic by loading and running it in the hardware simulator. So let's start playing. Okay, so this is the class quiz. Let me take a pointer. Okay. So dear students, in the last session we designed a single bit logic unit, if you remember. And today I want you to write the HDL for a single bit arithmetic logic unit. Other than the and the OR logic operation, this single bit ALU also performs the arithmetic addition of the two inputs A and B along with a carry in. Out of these three operations, which result is actually placed on the out pin depend on the selection of this multiplexer. I have given you this stub file for this bit ALU, and note the chip interface having four inputs, three single bit inputs A, B and C in, and an array of 2 bits for select input of the multiplexer. Similarly, note the chip interface has two outputs, an output pin which will contain the final result, and the carry out pin which will contain the carry out of the full adder chip as shown over here. So please stop this video, write down the implementation of this chip and then join me. Meanwhile, I am moving ahead. Well, this slide shows different components of our computer system which we actually have to design one after another in this part of the course. And we all know that the central processing unit is actually composed of three components. The arithmetic logic unit, which performs all the arithmetic and logic operations on different data items present inside the memory. And then the CPU also contains a set of registers which are used to store the data items to be operated on by the ALU, as well as store the results temporarily over here before writing them back to the memory. And finally, the third component of the CPU is the control unit, CU, which is responsible to move the data items from one component of the computer system to the other. And today we are going to design this chip, the arithmetic logic unit chip for the hack computer. So I will restrict my discussion on the ALU only. So let's move on to the design of the hack ALU. Okay, so dear students, this slide shows the interface of the arithmetic logic unit. It has two data inputs that can be of 16 bits, 32 bit or maybe 64 bits. Depending on this input F, the ALU perform one out of a family of predefined arithmetic and logic functions on these data items. The arithmetic functions performed by an ALU can be integer addition, subtraction, multiplication, division, and so on. And while the logical functions can be NOT, AND, OR, XOR, and so on. Now, which functions the hardware designers want the ALU to perform and which they want to leave on the software layer is of course a hardware-software trade-off, and of course a major design decision as well. Let's be a bit specific and talk about the interface of our hack ALU. Okay, dear students, our hack ALU will operate on two 16-bit signed numbers stored or represented in 2's complement encoding scheme, which we have discussed in detail in our previous sessions. The output of the hack ALU will also be a 16-bit 2's complement value. The function or operation which our hack ALU will perform on the two input bits X and Y is determined by these six single bit inputs to the ALU. We will be referring these 6 bits as the control inputs, which make up the part of the instruction given to the ALU. Based on these 6 bits of instruction, our hack ALU will perform one of these 18 functions as shown over here. Well, you can see our hack ALU can perform a bitwise OR, can be seen at the bottom, X bitwise OR Y, as well as bitwise AND. It can perform subtraction, addition, increment, and so on. So these are the 18 different functions which I will be talking about in a bit more detail on the upcoming slides. And which of these 18 functions this ALU is going to perform is dependent on these 6 control bits. Finally, other than this 16-bit output, there are also two single-bit outputs, namely ZR and NG. ZR stands for zero flag and NG stands for the negative flag. I will talk about these 6 control inputs as well as these 2 flags in the upcoming slide. And let me move ahead. Dear students, although there are 6 control bits and we can have 2 raised to power 6, that is 64 unique combinations that can be made from them. But since our hack ALU is required to perform only 18 different functions in this shown in this last column, uh, so we have just 18 unique combinations which will map onto the particular operation shown over here. Uh, Let me talk about these 6 control bits one by one. ZX stands for 0x. That means 0 out the 16 bits of the X input. NX means not X. That means perform a bitwise not of the 16 bit of this value. Similarly, ZY means 0Y. NY means not Y, and this F is used to do either the arithmetic add operation or a bitwise AND operation. This NO uh, perform a negation of the output is uh, if set at perform the bitwise NOT of the output operation. So let me move ahead and see if I have a more descriptive slide showing this. Yes, I have one. So dear students, before you uh, select the operation using this F bit, uh, you need to do the presetting on the X input and the presetting on the Y input, and then you perform this function F. And after you have done this, you perform a post setting, and finally you have this out. So 1, 2, 3, 4, 5, 6. These are the 6 control inputs which are given to this ALU, and based on these 6 control inputs, the ALU perform different operations on these two 16-bit values and generate this 16-bit output value, and also set or reset these two single-bit flags. Let us understand these 6 control inputs one by one. First of all, if this ZX is 1, That means make x is equal to 0. Make all the bits of the input x to 0. That means 0x. If this control input is 0, then we do nothing. Similarly, if this nx bit, not x bit, is 1, if nx bit is 1, then perform a bitwise NOT of the x variable. And if this nx bit is 0, then do nothing with the x. Similarly, zy will 0 out the 16 bits of y, ny if set will perform the bitwise NOT operation of y. And after doing any of these four operations, we reach on to this f bit. If this f bit is set to 1, then the ALU performs the arithmetic addition of x and y. And if this f input is 0, the ALU performs the bitwise AND operation of these two values of x and y. Finally, this post setting negate the output. If this NO bit is 1, then we negate the output. Whatever we have achieved over here, we negate it. And if NO is 0, we do nothing with this output. And finally, this is output. So I've tried to describe it quickly. If you have understood it, it is fine. If you have not, I will recommend that you should uh, re-listen this part of the lecture before moving ahead. So this slide gives you a bigger picture as to how the different combinations of these 6 control bits make the hack ALU perform one of the 18 different operations. These are the 18 different operations. So let us understand some of these operations one by one, taking sample input values. Okay, so let us first see how the hack ALU perform a NOT operation on the 16-bit input value in X. Suppose, well, this is the row we are interested in right now, the NOT X operation. If we want the ALU to perform a NOT X operation, the 6 control bits should be 001101. By that I mean we need to place a 0 in ZX, a 0 in NX, a 1 in ZY, a 1 in NY, a 0 in F, and a 1 in NO. Suppose that we want to do this. We have set these values, control bit values. The X is 1100. To keep things simple, I have taken just 4-bit values instead of 16-bit. The Y is 1011. So we don't have to do anything with the X. And since this 1, we have a 1 over here. So that means we have to make y is equal to 0. So we have to make y is equal to 0, and then since this is also 1, so that means we have to make it a NOT. So once we do a y is equal to 0, we get all zeros, and when we make y is equal to NOT of y, we get all ones. So we have y is equal to 1, 1, 1, 1. So after these two bits have performed their operation, there is no change in x. You can see 1100, 1100. And after these two control operations, you see the value of the y is 1, 1, 1, 1. After that, f is 0. So if f is 0, that means we need to do x and y. So if I perform an x and y on these two values, I get 1, 1, 0, 0. And finally, since this NO bit is also 1, so we need to negate the current value of out, and the current value of out is this. We need to negate this, so 0, 0, 1, 1. And you see the NOT X operation has been performed. The X was 1, 1, 0, 0, and now the value of output is 0, 0, 1, 1, which is NOT of X. So this is really great. Please repeat this part before you move ahead. Let me give you another example in which we will see how the hack ALU perform y minus x operation on the two 16-bit input values. And in the table for y minus x, the control inputs are 0, 0, 0, 1, 1, 1. And let me take sample values. Let's suppose that x is 2, 4-bit binary representation of 2 is 0, 0, 1, 0, and y is 7, 0, 1, 1. And now since zx is 0 and nx is also 0, so we do nothing with x. So x remains the same, 0, 0, 1, 0, 0, 0, 1, 0. However, as far as the y is concerned, the zy bit is 0, so we don't zero out the y bits, and the ny bit is 1, so we negate y. So we have y as 0, 1, 1, and when we negate this y, we get 1, 0, 0. And now we are going to perform the function f. Since f is 1, so we need to do x plus y. So if I do x plus y, I get a 1, 0, 1, 0. Okay, fine. And then since no is again 1, so we bitwise not the value of this out. So we get a 0, 1, 0, 1 bitwise not of this. And this is of course 5. And of course y minus x, 7 minus 2 is 5. So this y minus x operation has been performed on these two 4-bit values of x and y by keeping the control bits to 0, 0, 0, 1, 1, 1. That is great. Okay, so similarly, let me do another example, and that is x minus y. If you see the appropriate row of x minus y in this table, we have the control bits as 0, 1, 0, 0, 1, 1. Let me take the two values of x and y as 5 and 3. Since the zx is 0, so we don't zero out x, and since nx is 1, so we negate x. If nx is 1, then we negate x. So we have 0, 1, 0, 1. We negate it to 1, 0, 1, 0, 1, 0, 1, 0. As far as y is concerned, since zy and ny both are 0, so we do nothing. So y remains as it is, 0, 0, 1, 1. So the presetting has been done. Now let's see the function f. Since it is 1, so if f is 1, then we perform the addition, x plus y. So once we do x plus y, we get a 1 over here, a 1 over here, a 0 over here, and a carry, and a 1 and a 1. So this is 1, 1, 0, 1. Once we bitwise plus these two 4-bit values, x and y. And finally, since this NO is also 1, the negate output is also 1. So what we do is we negate the output. So we negate the output 1, 1, 0, 1, 2, 0, 0, 1, 0. And this is actually 2. And x minus y operation has been performed. X minus y, 5 minus 3, which is 2. Wow, that is really great. I strongly recommend, dear students, that you all must practice this on a paper and pencil. This working is very important to have a clear understanding of these 18 different operations that our hack ALU can perform. Okay, now that we know as how to do these two 16-bit input values, we can perform different functions and generate the output. One last thing that is left is how these two flags are set by this ALU. Well, as far as the this zeta bit is concerned, this is also called the 0 flag. The ALU sets this 0 flag or zeta bit to 1 if the 16-bit output is 0. If this output that the ALU has generated is 0, then the ALU set this flag to 1, otherwise it remains 0. Similarly, this NG bit, also called the negative flag, is set by the ALU if the 16-bit output is negative. If this output is negative, so this NG flag is also set. Well, these two control bits will come into play when we will build the complete hack computer architecture, inshallah. Uh, and let me say, dear students, that the design of this hack ALU is really simple and elegant. And to implement this ALU, you need only to know how to set a 16-bit values to all zeros, how to set a 16-bit values to all ones, how to negate a 16-bit value, and how to do a plus and an AND operation on two 16-bit values. And that is it. So it is really a very simple and elegant design. Okay, so now we are very much equipped with all the required knowledge to write the HDL of our hack ALU chip, which can perform one of these 18 functions according to these six control inputs, namely ZX, NX, ZY, NY, F, and NO. And in addition, the hack ALU also sets the ZR bit and the NG bit to 1. It sets the ZR bit to 1 if the result is 0 and sets the NG bit to 1 if the result is negative. So this is the summary, uh, and this is what all we have to do while implementing the chip logic. That is, if Zx is equal to 1, we place a 0 in x. If Nx is equal to 1, we negate x. If Zy is equal to 1, we place zeros in y. If ny is equal to 1, we negate y. If f is equal to 1, we perform 2's complement addition, and if it is 0, we perform the bitwise AND. If the negate output is 1, we set out is equal to not out. And finally, for the flags, if out is equal to 0, we set the 0 flag to 1, and if out is less than 0, that is, it is negative result, we set the NG flag to 1. Okay, so this is the code. You see the chip interface first. We have two 16-bit inputs, X and Y, and six single-bit control inputs, which determine the operation of the hack ALU. And in the out part, we have one 16-bit output and two single-bit output flags, the ZR flag, 0 flag, and the NG bit, the negative flag. And also please go through the code in the implementation part, which I think will make sense to you all. And that is it. This is the complete code of the hack ALU. And let's now move on to the terminal and verify the working of the hack ALU chip. The hardware simulator is already running. Let us load the ALU chip by clicking this load chip button. Well, dear students, you can always load the ALU chip which we have designed right now, which is there in the directory number 09 in the lecture codes format, in the lecture codes directory, which I have already uploaded in the course Bitbucket account. But let me move on to the tools directory, and inside the tools directory, let me move on to the built-in chips directory, and let me load this HDL file, the ALU.hdl, the built-in chip. Let me click this load chip button. Okay, you can see once we load this built-in chip, we have a GUI side effect as shown over here. Since this built-in chip is implemented as a Java class in the hardware simulator, so it has an additional GUI effect, which is really cool and makes things easier to understand. Over here you can see the chip interface, and well, in the implementation part you can see this is a built-in ALU. Okay, so Let us first instruct the ALU to perform our logical AND operation. Suppose. Remember, these are the input pins X, Y, two 16-bit numbers, and these are the 6 control inputs which are going to decide what operation this ALU is going to perform. And since we want to perform a logical AND operation, the 6 control bits for the AND operation are 0000000, and we have already set these values over here. You can check these values, of course, from the table. No need to memorize them. Let me place 15 in the X, and let me place 100 and let's suppose 40 over here. And since we are going to perform a bitwise AND, so let me change the format from here from decimal to binary. And now let me click this eval button, and you see we have done the bitwise AND of these two numbers successfully. You can confirm this. I have already confirmed. Anyway, let me do not Y operation. Uh, and you can always see the 6 control bits for performing not Y operation are 110001. So I need to change these control bits 110 and then 001. Once again, don't need to memorize them. So the control bits given to the ALU now are for the operation not Y, and Y is 140. Let me change it to binary. So this is why once I will click the eval button, you will notice that this will be negated, and here it is. You see, this is negated. The Y value, 16-bit of the Y value are negated over here. And moreover, since we deal with the 2's complement representation, so it is apparent from this bit that this is a negative value. Let me change it to decimal. You see, this is a negative value. And since the output is negative, you can see the ALU has also set the NG flag to 1. The negative flag has been raised that the output is negative. Okay, so let me do X minus Y now. X minus Y, and for X minus Y the control bits are 0 1 0 0 1 0 and then 0 1 1. So 0 1 0 0 1 1, these are the 6 control bits. This combination is required to perform an X minus Y operation, and if I perform a X minus Y operation, I think the answer should be, well, yes, minus 125. And since the answer is minus 125, you can again check out that the negative flag has been raised. Let me change the value of X to let's suppose 140. So now X is also 140, Y is also 140, and let the control bit combinations remain the same, and that is 010, 011, which performs X minus Y operation. And now when we will perform the X minus Y, we will get a 0 output. Let me check this out. Yes, the output is 0. And since the output is 0, the ALU has also set the 0 flag to 1. Since the output is 0, so the 0 flag is also set to 1, while the NG bit is set to 0. So the answer is not negative. Meanwhile, you must also have observed the GUI values shown over here as well, instead of looking into this output pin pane. I think that is enough. I strongly recommend that the students must practice different operations on different data values to verify the chip logic, and building your own concepts at the same time. And let me fall back to the slides. Okay, so this slide shows you how to load the ALU chip and run it. Okay, dear students, that is all for today's session, and these are the tasks you need to do. Please do a lot of practice so that you should have a clear understanding of the working of the ALU. And I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.